Is it visible? Slide is visible to you?
Yes, ma'am, it is visible.
Okay. So please let me know if stuck somewhere. Please let me know. Okay. It's now in the full screen.
Yes, ma'am, it's full screen.
Okay. Okay. So should I start?
Yes, ma'am, you can start.
Okay. So once again, welcome to the presentation. So as given the topic, drilling and fracturing of shale wall and tight reservoir, shale and tight reservoir. So already Professor Singh has mentioned about what you mean by shale and the tight gas. How can you classify those, right? Is it? I need your response. No? Okay. So the presentation preview, if you look into this, I'll just little bit brief about the shale oil and gas and tight gas. What is the Indian scenario we have, and the formation characteristics, the permeability variation, what are the properties we need to consider for fracturing and drilling. Then how do you select the fracturing fluid and drilling fluid? Then types of oil we use for shale and tight reservoir, a need of hydraulic fracturing stages, and the type of fracturing fluids. Okay. So please let me know, stop anywhere if you'd like to have more explanation on this. So just to tell about like why we should go for shale oil and tight gas, tight reservoirs, right? Now we are moving towards the transition, energy transition, and energy basket. We want to reduce the conventional hydrocarbon. But if you look into this, more than 80% of our energy requirement we fulfill from conventional, and the conventional reservoirs are depleting first. But if you look into this petroleum resource triangle, you can see though the conventional oil and gas production is easier because of the good quality of reservoir, but the amount of volume of oil and gas we have in unconventional is huge. And the shale oil, shale gas, and the other unconventional, they fall into the mid category of middle of the petroleum resource triangle. So we need to try to produce more from the unconventional reservoirs, oil and gas both. So, but the cost, if you look into this, this is as per 2024 data, the break-even cost of oil production is average like here, it's about $26 per barrel. Onshore Middle East, it's $27. Continental shelf, about $37. Deep water, it's 43, and tight oil, if you look into this, 45. Shale oil or shale gas is the boom in USA, and that changes the global geopolitics, petroleum geopolitics, you can say. That is that ensures huge production and supply of oil and gas from the shale and tight reservoirs. Shale oil cost is more than about $35 a barrel as per the calculation in 2020. So if you add 26 plus 35, it's coming around 61 barrel per dollar. Then also we can have today's price, if you look into like about $70 a barrel, $10 a barrel profit will be there. So we need to, if we want to make more profit, we need to go for the EOR in shale oil, or you have to improve the productivity of the well. And that in that, the drilling and fracturing play a very important role. The optimization and well designing of wells and fracturing is very important. Just a little bit about shale. Already, Professor Singh has mentioned this is the clastic sedimentary rock. It's composed of mud, a mix of flakes of clay minerals, and tiny fragments of other minerals, especially quartz and calcites. These are very important parameters for our fracturing of the shale. Unless otherwise you know this rock mineralogy, you cannot do the fracture. We'll discuss this in when we'll discuss about the development of shale oil and shale oil field development. That time I'll discuss in detail. So shale is characterized by breaks along the thin laminae or parallel layer. So if you look here, if you look into here, you can see the parallel layers are there. This is shale oil, some picture from the shale oil. So this shale is formed of compaction of silt and clay size particles. Shale and mud rock contains roughly 90% of the organic matter in all sedimentary rock. So it's if we look into this, like we have in shale properties, we need to that control the rate and volume of shale gas, that shale gas and of course shale oil, thermomaturity, gas in place, total organic carbon content, reservoir thickness, and proportion of absorbed gas or free gas and oil there. This characterization, if we look in, if we think of this, this is the most abundant sedimentary rock, accounting about 60% of the sedimentary rock. And most importantly, whatever oil or gas we are producing, that's from the shale itself. So shale is the petroleum source rock. So anywhere we find the oil or gas, we must have the shale. So generally, certain amount we have studied the migration characteristics. So after the primary migration, certain amount of oil and gas remain in the shale, and that we can produce by advanced technology, that oil and gas we can produce, and that could fulfill our energy basket. But the huge uncertainty because of the heterogeneity, variation, and depositional sources and environment, there is huge uncertainty remain in that. It's less economics, as I had mentioned. So it needs huge packaging because of the very low permeability, environmental impact because of huge fracturing of tight rock, shale, sandstone, or whatever may be. So it may cause the environmental impact. So that's why there is some debate in hydraulic fracturing in USA or UK. So you need to look into that when you go for the fracturing or drilling of the wells. And globally, if you look into this, this is the United States, this much amount of crude oil in shale oil. Shale gas is there, crude oil are equivalent. This is an wet natural gas. This is in United States. This is outside United States. And this is the global shale oil and gas. So this is the production scenario in India. If you look into this, we are not producing any shale oil or gas. This extra heavy oil also we are not producing. Mostly our reservoirs we are conventional in nature, but in tight gas reservoirs. And shale, we have huge shale. I'll mention about what there. If you look into US production, you can see the shale gas production is very large. So here also oil is there. Shale oil play this one shale oil in this is in USA. This is in China's production. Here they are not producing, they are producing. So these are the characteristics of this. In India, we have the shale and this basins we have. In Rajasthan, here we have in Gujarat, Cambay Basin, Mumbai offshore. Everywhere, wherever we get oil and gas, as I had mentioned, and reservoir rock, there must be the source rock, that the shale should be there. So these are here also, wherever we get oil and gas, shale is there, but still we are not producing well. In this area, we can have shale oil, shale gas could be there, estimated. In this basin where Damodar Valley Basin, we have the shale gas. This Assam Arakan also we are not producing here because of the uncertainty and the proper studies, lack in proper studies, we are not producing. That necessitate the production of oil and gas. This production from shale oil and gas. So these are the tight oil in India. As I had mentioned here, in addition to that, we, as you know, that shale oil could be found in shale, which is not very much matured enough. At the initial stage of maturity, we can have the oil. When the maturity improves with time, the oil could be converted to gas, and we can have the shale gas. So this in Ganga Basin also, we can have some tight oil, which is mostly in the shale itself. So this could be now also government of India has taken up these projects to explore these areas. So now let us consider the characteristics of the shale or tight gas, and why was the need of fracturing there. So if you look into this scale itself, so this is the permeability level. So this in conventional oil and gas, if it be oil, we can have more than 20 millidarcy, then we can have the oil, no fracturing may be needed. But if it be less than, of course, depending on the viscosity of the oil, if it be less than 10 milliliters, even for gas also, some fracturing may be needed here. So this tight gas, here we can say this one is the tight oil here. And tight gas generally it's up to the 0.001 milliliters. And unconventional tight gas also, sometimes we call that unconventional. So that this permeability level will be much less. And this shale, if you look into it, it's in between this one. So it's in terms of nanodarcy level, the permeability varies like this. And the soft tight gas, we classify this depending on the permeability and porosity variation. This is the porosity scale, permeability scale. So this 1 and 2, this is the soft tight. This is the tight, where we have permeability variation is 0.1 to 0.01. So these are the tight oil and gas reservoirs for which extensive fracture is needed. So these are the, already had mentioned those, this one where we can have in KG Basin, Kaveri Basin, Kambe, Vindhya Basin, these are the activities we have for the tight gas. So production challenges in the gas and oil, this low permeability, because of low permeability, artificial stimulation like hydraulic fracturing is needed. In addition to that, we need to have special type of oil that generally horizontal or deviated wells are needed to have the higher SRV, stimulated reservoir volume, and the drainage area. Okay. So, but at the same time, we need to consider as the permeability of the tight reservoirs and shale reservoirs are very less. So their pore diameter also comparatively less. And there we need to be very careful about the formation damage, because drilling fluids and fracturing fluids need to be selected properly so that fracturing could be avoided. Damage of the formation could be avoided. If there be damage in the this formation, then even after fracturing also, we can have the reduction in the permeability and the production rate. So here, if you look into the fracturing, we need to know what kind of rock permeability we have, what are the water sensitivity and mineralogy, natural or induced fracture we have, that we need to consider. For drilling, generally, we need to drilling pits and the type of drill pit. These are very important. In addition to that, well completion and type of well is important to get the better productivity, enhanced productivity of the well. So this one, when we talk about the drilling fluids, as you know, the functions of drilling fluid, that's cooling and lubrication, cutting of removals, formation pressure control, wellbore stability, hydraulic energy transmission, minimizing formation reservoir damage, improving drilling rate. These are the characteristics of the drilling fluid. These are similar to the conventional reservoir. But when you talk about the reservoir damage and water sensitivity, these are very important, and the well stability. For shale, when you drill the conventional well, that time also we need to take care of the shale formation on the top or at the bottom of the formation zone. Here, as we are drilling the formation, those show well stability, cavings problem, and this as we have the good amount of clay, so swelling problem also to be taken care of. Uh, if we talk about the drilling fluids, we need to consider the drilling fluid and type. Here, generally, that shale, as I had mentioned, this is cost is very high compared to the conventional one production cost. So break-even production cost is high enough. So when you when you produce this drill this well, so type of fluid and the properties are very important. Selection is very important. In general, we don't use like heavy mud here, because the formation pressure itself, like fluid pore pressure, is not so high, though the total pressure as we are drilling more than 2000 meter or 3000 meter depth, the temperature and the pressure total overwater pressure is high there. So rheological properties also to be considered because of the temperature consideration here, and density, pressure control, filtration, and solid control is very important here, because shale generally is having the natural fractures. Those though are very less in number, but and depends on the maturity of the kerosene. But there may be filtration loss, so we need to consider that one. So if you look into this drilling, generally foam drilling could be a good one, and we also use the other like slick water and others, but huge amount of water is needed to that, and we need to take care of the clay swelling and this stability enhancement chemical additives we need to add here. Drilling generally, when we drill the wells, so because shale is having very poor permeability, so to have the higher drainage area, mostly we drill the horizontal well. So this is for the tight oil, this length of this tight oil, because of the less extent of the reservoir, it may be less, but for the this shale oil or gas, we may have large, the length of the leg maybe much higher in terms of miles itself. So so when you talk about the drilling of oil and oil density for full development well, if you look into here, so in shale we have the this natural fracture, which is shown here. This one, the mini fractures are there, and we need to do the fracturing. So well should be placed properly, so that this fractured should be well connected to the well, like this fracture connection. This is the matrix connection. Matrix we are connecting, and these are the fractures we are connecting here. Fractures we are connecting, so that we can produce well. So here the well spacing the number of wells and the well spacing depend on like stimulated fracture permeability of the reservoir, and matrix and fracture connectivity or viscosity. You have the economics, there's other consideration. So here is one example. If you look into this, the single well production rate and the cumulative production rate. This is cumulative production rate of single well. Like here, if we look into this with time, the historical data is the blue one. So with time, the single well production rate is keep on declining as usual, like the conventional one. So for different spacing, initially it does not impact on the production, even in the cumulative. production. But when you produce for longer period, if you look into this, this is the rate one is the 300 well spacing, this is 350, and this is 400. So here you see 350 is the optimized well spacing, and that depends on but cumulative production, if you look into this 400 well spacing, give you more cumulative production, but that may not be economical. That's why this 350 may be optimized well spacing. So these are depending on your the fracture connectivity matrix and fracture connectivity, permeability, and the oil viscosity itself. So drilling, we can not only the horizontal drilling, we can have different other types of drilling also, this multilateral drilling. So multilateral, maybe we can have this, this is very specific one that we use for the attic well if you have left some oil here. So if there be oil from the shale may not be migrated and pool of oil may be often here in the attic location, then we can have this kind of two lakes. We can have multilateral well. So these are the naturally fractured. This generally multilateral well, we can use this for the naturally fractures and induced fracture. We have the layers then because in shale we can have very thick layers also. So we can have thick layers, but in between we can have the laminae. So this we can have this kind of layered wells also we can drill. So this could be used for this enhancing the production. So here when we talk about the production drilling of well, so completion is very important here because we move through different this water layer during the production of oil from the shale, which is deep enough, as I have mentioned, 2 kilometer, 2.5 or more than that kilometer depth we are producing here. So if there be any leakage, because it's producing from high pressure to low pressure, there may be leakage, and this water table may be contaminated, which is a big problem, and people are debating about this and wanted to stop the shale gas or oil production because of this contamination of the water. This is an environmental issue. So here we need to have good this completion should be good enough, casing and cementing should be leak proof, so that there should not be any leakage from this to the water table itself. So this is, as I had mentioned, this we should have the leak-free well we should have. And cement design needs to be studied both for its liquid properties during the pumping as well as the mechanical strength and flexibility after setting of the cement, because there should not be any leak. Yes?
बोलिए मैडम क्या हो रहा है?
Yes, please.
ऐसे ही कुछ काम कर रहे थे लैपटॉप पे. नाश्ता कर लिया? नाश्ता कर लिया.
Hello, Siddharth? Yeah.
Yes, ma'am, we are muted.
It's okay. Thank you. So this setting time of cement is crucial factor because you are drilling in a very large depth also. So there should not be any leakage. It should be leak free, as I had mentioned. So it should be selected properly. In addition to our multilateral well, the drilling pad is used so that we can utilize minimum land for the this minimum land for the production, as well as deforestation or other problems could be sorted here using this. So here generally we can have this rectangular drainage area. Rectangular, and this is lures. You can see here the spad wells. These are the wells we have. This is deviated well, and this is fractured in the both the sides itself. Okay, so this reduced number of horizontal wells needed, coupled with the ability to drill multiple wells from a single path. it has significantly reduced the surface disturbances and associated impact to wildlife, dust, noise, and traffic. Okay, so for example, if we can have a vertical well may only drain a cylinder of shell 1,1320 feet in diameter and as little as 50-meter high. By comparison, a horizontal well may be extended 2,000 to 6,000 feet in length and drain volume it's much higher here. Okay. So this what did you had mentioned here, like how we can improve the reduce the this butter surface disturbance, but increase the production from as a single well fed. This one is the advantages of the well pad. Now stacked well is the another provision because of shell. As I mentioned, there are a number of layers may be available for this. So from a single pad we can have the stacked well, so one after another in stacked like this we can produce. So stacked well is the another example of enhancing the production from single pad itself. So this is used in the Pearsall and Eagle Ford place in the southern Texas. So this has improved the efficiency of the production hugely. So this is different. The other example of Permian Basin, you can have this kind of stacked well, which can improve the production to huge large extent from a single pad itself. These are the examples of the multilateral well. You can have this kind of 3D wells also. These are the different types of multilateral wells. Multi-branch well, cluster multi-branch re-entry. So if there be any fault like this, you can have this kind of well. A stacked well I mentioned. This is 3D well and multilateral wells. So next is the as I had mentioned, permeability is in terms of tight gas. It's in microdarcy almost 0.1 millidarcy to and less, and your shale is in nanodarcy. So fracturing is very much needed. Without fracturing, we cannot produce. We cannot enter into the oil, and the oil cannot flow through this small, tiny natural fractures itself. If you look into this shell, first shell was drilled in Fredonia, New York in 1821. First structure well is 1947. So these have changed the game of the production of oil and gas. And now we can produce most of the wells. These are old wells in the conventional reservoir or in shale or tight gas. Without fracturing, we cannot do any production here. So and this here generally in this shale gas, we do fracture using the sleek water mostly, and this is one of the problem to use huge quantity of water is needed to fracture the shell itself, shell or tight gas. So generally sleek water, if you use the sleek water, more than 98% of the fracturing fluid is water itself. So reduce the dependent on water. Foam is the another option, or VS could be the another option for this purpose itself. This is one this. If you look into this video, this is animation itself, not the video. This tells how we do the fracturing. So if you look into this, this is the pad fluid is being injected first, so to initiate the fracture. So the yellow fluid, this is the pad fluid. So this is injected first to initiate the fracture, and then the propellant is being injected along with the pad fluid. So this we called as the fracturing fluid. So fracturing fluid contains this the fluid plus the propellant, and then once you place the propellant, then we need to inject the displacing fluid to clean the fracturing fluid and clean the formation. Then to make it, and then flow back the displacing fluid to make it, to make the reservoir ready for the production. So here, if you look into the propellant I have mentioned before. So these are the solid particles, maybe as sand or some other particle, lightweight, heavyweight sand, depending on the your stress level and the formation you have. And it may be resin coated or otherwise some other coating may be made to make it usable in different formation condition itself. And the other properties of propellant, that it should be strong enough to bear the overburden. It should not be crushed. It should be lightweight so that it can flow with the fracturing fluid and it can be placed far away from the wellbore. So far away from the wellbore, if you the previous slide, if you can see here, we are putting here, so it should move through the formation as per this fracture length should be filled with the propellant, so that propellant can prop up the fracture. It should not close after taking out the fracturing fluid after completion of the fracture. So this should be, in addition to that, to enhance the permeability of this formation, we generally opt for the regular shape and round shape, spherical shape propellant, so that the good sphericity will improve the permeability. They should not be, and they should be of uniform size. If we have small and large size, they can reduce the permeability. So if you look into this, these are the properties of improving the permeability and porosity. If they are well sorted, then permeability should be improved. They are ill sorted, then permeability will be reduced. So this should be taken care of when you are selecting the rock, the propellant size, shape, and selection of the propellant. Okay, so in addition to that, this propellant should be carried out by the fracturing fluid. So this fracturing fluid plays important role in efficient fracturing of the shale or a tight gat itself. So it should be compatible with the formation rock, must be compatible with the formation fluid. Whatever fluid we have, this is oil or water, both if we have, they should be compatible with that. It can generate sufficient pressure to drop down the fracture to create a wide fracture. So it should be wider one. So wider the fracture, you can have the fracture SRV, stimulated reservoir volume could be higher. It must have the sufficient low viscosity to allow the cleanup after the treatment itself. So when you're placing it, then after placing, if the fracturing fluid remains here, generally in fracturing fluid, we have the viscosifier. Viscosifiers are mostly the polymers. If it remains there, they can plug the pores itself. So you have to remove this plug, clean these pores so that your permeability should be enhanced. And it must be cost effective. That's why, as mentioned before, the slick water is used before energized water, or water, huge amount of water is used to place this. But in addition to that, we have the viscosifier and other properties will be here. So water-based fluids are commonly used, and slick water is the most common fluid for shale gas fracturing, shale oil and gas fracturing. Okay, so in addition to that, the other chemicals, we add the surfactant polymer, so that reduces the surface tension and friction. Probably Professor Singh will discuss on that fracturing fluid and surfactant in the wettability changes here. He will discuss that. Other fluid, we can have the oil base if we have the clay, and this is very sensitive one. Though we use the different KCl or other clay stabilizers, then also sometimes it's very, if it be very sensitive, we need to use the other oil-based mud also, or foam fluid, which can reduce 80% of the, more than about 70 to 80% of the water use of in in like compared to the sleek water itself. So other chemicals we use, the acids to clean the shell to improve the gas or oil flow, biocides to prevent the organisms from growing and clogging the shell fractures, corrosion, scale inhibitor to protect the integrity of the well, gels or gums that added the viscosity, friction reducers. These are the other additives to the fracturing fluid itself. So this hydraulic fracturing, that depends on the uncertainty of the reservoir. Like if the this heterogeneity of the reservoir is huge, then you need to consider how to do the fracturing and like what kind of fracturing fluid you can select and how effective would be the fracturing. Many cases it is observed that if your fracturing design said you can have 300 feet of fracture half length, but later on you can see if it may be 20 or 25, it may be of 100, I'm sorry, it may be of 100. And in addition to that, fracture width is also not so good. So ultimately the fracture SRB may not be very high. So in that case, we need to take care of all the parameters well so that we can have the treatment design could be economic for production of the desired production rate of oil and gas itself. So optimization of the critical fracture parameters, that's fracture spacing, fracture half length, and fracture conductivity, that generally control the well performance, and we need to take care of these parameters itself. Yes. So, as we have seen, we have the long well in the shell itself, shell or tight gas, to reach to the large area of the reservoir itself. So, single stage fracturing is not good enough to reach the reservoir. So in this case, generally, we do the multi-stage fracturing. So multi-stage fracturing, when you do, generally we carry out the fracturing stage-wise, one stage in a time, and then plug that side and then do the fracturing of the other side. So if you start with this, so first you do the fracturing and then plug it here and then the fracturing here and then fracturing here like this. So multi-stage fracturing is conventionally practiced in fracturing of the shale and tight gas reservoir, so that we can reach, if you look into this one, if you look into this, so you can have the large SRV you can have here. Excuse me, just a minute. Sorry. So here, if you look into this, typically several million gallons of fluid composed of 98 to 99% water to water propant, and the propant is pumped at high pressure in the well. The rest of the fracking fluid that contains about 0.52% by volume is composed of the blend of chemicals and other properties, as I had mentioned here. So Barnett shale, this typically this one example is here, the Barnett shell. The reservoir exhibits a net thickness of 50 to 600 feet, porosity about 28%, and total organic content 1 to 14%, which is very good. found at depth of 1,000 to 13,000 feet. So here the spacing was for the fracture spacing varies from 100 to 700 meter in actual hydraulic fracturing operation in three burner shells. Also, the productivity of burner shell is highly dependent on the completion method implemented and large fracturing treatment. So in this, like when we are talking about all this here, so in fracturing, one more parameter is very important, like the mineralogy, as I had mentioned. So if you are going to do the fracturing, this mineral matter should be good enough. If you have high clay, in that case, the fracturing could not be, your fractured length could not be good enough. So there, the mineralogy, generally the calcite, sandstone, this quartz, that should be large quantity, so that frackability could be improved, frackability could be higher, and we can have the fracture half length could be good one. So when you are selecting the sweet spot for hydraulic fracturing, so this the mineral matter content should be determined first, and their stress analysis should be done so that we can have the fracture trackability could be good, and we can select the shell for the further production or for the development itself. So there are like some questions I have made for you, like if you go for the shale oil or gas production or tight oil and gas production, what are the difficulties you can face here? So what kind of difficulties you should face? So I need the answer, like it's not like one way, so it should be discussed further what we have discussed. So all the participants, please, I'll ask the questions and then I need the answer. That's why I have completed it first so that I can interact further. Participants, please. Please reply. Am I audible to you?
Yes, ma'am. Yes, ma'am.
So tell me, what are the difficulties in production of tight reservoirs and shale oil or gas? What difficulties we face? Difficulties in first thing?
I guess first question.
Yes, please.
So, Kevin, can you come this side?
What is the main difficulty?
Okay.
Why it's not economic so much?
Low permeability.
Low permeability. And
Yes, some of the difficulties which we face there is contamination, groundwater contamination during the fracturing.
during fracturing?
Yes, yes, yes.
So, as you had mentioned, fracturing is very important here, and difficulty in fracturing. One of the difficulty is the need of huge amount of water, right?
Yes,
Huge
yes.
amount of water you need, and
Yes.
you're fracturing at very high depth, large depth. So there, it's said, though this is controlled very well, but there may be some seismic uh, disturbance in the nearby, and controlling of the fracture is very important here. So otherwise, it could, as it mentioned, it could like people claim generally it could contaminate the water. So what do you think? Is it really happen, or there could be in hydraulic fracturing? How can you control that? How can you control the contamination problem?
Yes, in controlling the contamination, I think we need to make sure during the well completion also, the well completion is well monitored. For example,
Well,
make sure
monitoring,
that the cementing
see
is well, yes.
the control of the fracture length, fracture volume. That's very important, no? Control of the fracture propagation. So if you can control the propagation, then you must ensure that there should not be any leakage of your fracturing fluid to the other water body. In addition to that, if you look into the water body, generally where from we take the groundwater? Generally few hundred meter, only within few hundred meter, maybe 400, maximum 300 meter depth, not beyond that. And what is our shell? This is an more than 1,000 meter depth.
Yes.
So possibility of contamination during fracturing is not so high. Okay. It may be after the production, or as you have mentioned, the well completion, there may be any leakage in, as I had mentioned, casing or cement. That could leak too, but otherwise, no. Okay.
Yes. And also
There
during
should
the
not be.
flow back also.
Yes.
Flow
So
back
yes,
sometimes.
any other comment, or like, do you have anything else to say? Anyone else? I could see, I could hear some voice. Any other opinion? Do you have? So another thing, like when you talk, okay, another question. What the range of permeability in shale, tight oil and gas? Tight oil and gas. I had shown some scale. What is the permeability level in shale generally? And what kind of fractures we can see in the shale?
It should be 10 to 100.
Permeability.
Permeability. Now,
yes, permeability.
not into normal permeability.
From 10 to 100 nanodust. That's the range.
Okay. So, tight gas, tight reservoirs. The way we define tight gas and tight oil, where we need the fracturing.
Micro range.
You check the scale, it's tight gas, we start below 0.1 millidarcy, right? Okay. So if you do both the cases, tight, conventional tight gas, or if it be tight reservoirs, that may be sandstone, carbonate, or shale, it could be. So how the fracturing could differ in shale and tight reservoirs, conventional like sandstone or carbonate? Will they differ? Will they differ? If you do fracturing of carbonate or sandstone, let us consider the sandstone and shale, which will be difficult to fracture? Which will be difficult to fracture?
Shell.
What? Why shale? Why not sandstone?
Because there's some those rock properties.
Ma'am, shale is brittle in nature, so it is difficult to frac.
Yes, because of the mechanical properties, brittleness index of the sandstone will be more than the shell. Shell is having more organic component and clay compared to the mineral matter, where sandstone is having less clay and more like mineral matter. So that fracturing of sandstone is much easier compared to the shell. And in sandstone, generally we have longer fracture compared to, so the half length will be more for the shell sandstone compared to the shell. Okay. So next questions. What are the selection criteria of well type in shale and tight gas? How do you select different? What are the different types of oil we use? In shale or tight reservoirs? Shale is one of the tight reservoirs, of course, ultra tight, you can say. Whether you want to go for multilateral, single horizontal, or stacked well.
Horizontal.
When we go for single horizontal, think of this. Does it depend on the thickness of the shell?
Yes, yes.
Thin reservoir. Thin reservoir.
For thinner shale.
For thinner, you can have the single, and stacked well, we can have, if you have multiple layers, parallel layers. So in that case, you can have the stacked well, no?
Yes, ma'am.
If you have the thick one, what will do?
Multilateral.
Thick shell you have.
Multilateral.
Multilateral, then go for multi.
Very thick. Will you go for, it should be vertical well or horizontal well?
Horizontal. Vertical.
Which could be good?
Horizontal.
Vertical, horizontal, multilateral, very thick well you have. One single layer, single thick layer you have. Single thick layer like this is very thin layer like this. And this stacked one single layer, large.
Horizontal but multiple there.
Horizontal. Vertical.
Stacked horizontal wells we could.
Vertical with multiple fracture.
If it be thick, we should not go for very horizontal well, no? So fracture, what should be good? This way, fracture length in vertical direction, it should be high, no? Otherwise, you cannot extract oil from there. So in that case, single horizontal well, we can have the large perforation should be good compared to this one, no?
Yes.
With a fracture, that could be better. Or we can have one well with multilaterals. Many side tracking could be there. So that could be the choice, to my opinion. So cost of shale oil production, why it's high compared to the conventional well? How much high it is? How much high compared to the conventional as per the studies? If you produce of same viscosity oil from the conventional and from the shale, if you produce, the production cost should be higher in shale oil, right? So how much higher it is? How much higher? It's studied at $35 around, no? In addition to that, why this cost comes from where? Conventional oil and the shale oil.
And hydraulic fracturing.
Hydraulic fracturing and EOR, implementation of EOR. Why we need to go for EOR? I didn't, shale oil. What the oil remains in shale?
For
And
converting
how
to
much?
For
If
thermal
we have one conventional oil reservoir and on one shale oil reservoir, where we can have per acre, the barrels per acre could be higher in which case?
conventional,
Why?
because there will be more permeability, so we will be able to cover more area.
Permeability is responsible for per acre, like oil capacity or storage capacity or porosity.
Porosity.
Porosity, no? And during production, the permeability. So what is your pore diameter? Where it should be more? In shale or in sandstone? Conventional sandstone or carbonate? So their permeability variation will be there. Okay,
Yes.
so both without like implementing EOR technology and hydraulic fracturing, production from shale is really difficult. Production of oil from, so that's why almost double of the conventional oil production from the shale oil, no? So advantages of pad well conventional to the compared to the conventional vertical well. What are the advantages?
Cover more area.
What are the advantages of pad well? Nowadays, for conventional oil reservoir, gas reservoir also, we use the pad wells. From a single
Minimize the
pad, we have
deforestation.
multiple wells. Yes,
It minimize the deforestation.
yes, and pollution and the disturbances, low land acquisition. Okay, so these are the reasons you need less land, less pollution comparatively, and like if there is imparting less pollution to the environment in terms of your this deforestation or others also. Multi-stage fracturing. So why you do multi-stage fracturing?
If we have multiple layers of particular zone, then we need multiple.
No, when you are using long extension leg of your well, so single fracturing is not good enough to cover the entire area. So we need to go for the multi-stage fracturing throughout the leg. Okay. So multi-stage fracturing. How do you control that? Generally, one technology is used, though it's very costly, to control the fracture or fracture propagation. Can you name that? Fracture propagation, control and monitoring of fracture propagation is done by using one technology, that's the 4D seismic. That's very costly, of course. Not everywhere you can use to control the cost.
Yes.
Conventional drilling and fracturing fluid, but we use for the conventional. And what is recommended? Drilling and fracturing of shale, oil or gas. Tight gas, it may not be so effective, but for shale, oil or gas, we use slick water. Why? Why not conventional polymer-based drilling fluid or polymer-based fracturing fluid for drilling and fracturing of shale.
It's because of something of formation damage.
Yes, one of the reason is to prevent
when it is
formation
low,
damage.
when it is low viscosity, so we can pump it at higher rates.
But what could be the problem? What is the problem?
Shale swelling.
Water sensitiveness of shell can lead to.
What about the propant suspension and propant
We can
placement
carry
efficiency?
propants in a better way.
It's not very good, no? Water cannot carry very efficiently and place it very efficiently. But then also we use that water. Okay. So generally water density is less. Can you use this for conventional gas or tight gas? Can you use this? What problem will you face? Shale gas and tight gas, say you have. So in tight gas, can you use simple slick water wherever we are using slick water for this shale? Why can't we use? Why density is important for us? Drilling fluid density is important for us while drilling.
Provision of hydrostatic pressure.
Yes. So is there, what about the safety factor in shale? Shale oil or shale gas? What could be it? What are the reasons? 1, 2, 3, like this. 1, if we have the shale gas, in what state it remains within the shale? Mostly some free gas, some are adsorbed gas. So and in addition to that, the permeability is less before when you are drilling, the connectivity is very poor. So flow of gas is very less, right? So this danger of blowout, the safety factor is not so alarming here compared to the conventional or the tight gas reservoir, no? Do you agree or no? Okay. Do you agree with me or no? I'll stop here.
Yes.
Yes, ma'am.
Okay. So I could see one question and this. Okay. Thank you. Thank you very much. So we'll discuss next day about, please let me know whether you have the kerosene type and the maturity level is being discussed with you.
Yes, ma'am.
Shale characterization with the maturity level depending on the kerosene type, their temperature, oil and oil prone, gas prone zone. These are discussed?
Yes, ma'am.
Okay. Okay. Thank you very much. We'll discuss later on the other things. Thank you.
Thank you, ma'am.
Okay, thank you so much, ma'am, for this informative session.
Thank you.
So now we will have next guest, Professor Sayantan, sir. We will wait for 5 minutes.